Okay, hello everybody. How is everybody doing? So this is our second episode of the Science Saturday. We had the first one on visualizing airflows. Today we are going to go a little deeper in some of the optics ideas that we reviewed in the previous episode. So today I have a couple of helpers with me in the room. Here is my elder son Atharva Kapale, younger son Apurva Kapale, and we are all going to now take our masks off. We are in a room with just by ourselves, and there's nobody else, I think, in the building even, well, except for Dr. Wong, who is in his lab in the other room. So masks off so you can see us better. Atharva is going to help me show some of the optics demos that we have. The lighting conditions are a little tricky to manage when we want to show you optics demos going, and for that, we need to have a completely darkened room and need to manage the camera well. And it turns out the phone cameras are kind of the best for that. So there is some lessons in there as well. Optics is a little tricky to broadcast over a live streaming meeting like this. Okay, so again, welcome everybody. Thank you for your attendance today, and we will hopefully have a lot of fun. Another couple of nice things that are happening today. Two of our other faculty, with the help of two other students, so Dr. Araja, who is our radio astronomer in residence, and his student Natalie, they are going to show you a real telescope through a pre-recorded video. And then later on, Dr. Wong, on a live video, he's going to show one of his really cool microscopes. And he's going to show you some cells with the help of the microscope and the image projected on his computer screen. So that's kind of the plan. So basic optics demos from me, and then we're going to learn how to how those ideas apply to some real life equipment that you may encounter. Some of you may have already seen. So on the slide here, you can see 4 images on the right. First one is the image of an eye. We are actually, whether we realize it or not, optics is an important part of our everyday existence. The eye, our human eye works, and the optics of the eye is actually even more amazing than all of the stuff that I'm going to show you today. I am restricted in the focal length, the property of the lenses. I cannot change that as on a needed basis. Our eye can do that. So our eyes can focus on things that are far away when you're outside, and our eyes can focus on some really small things when, let's say, when you are reading a book. And so that lens, optics of the eye is even more amazing than what I'm going to be showing you today. The picture 2 here is the picture of a refracting telescope, and you will be seeing, the other kind today in the video later on. Picture 3 is it looks like a translucent cable, but it's actually something called a fiber optics cable, and the light entering on the left end, the loose end of the cable, is going in, passing through the cable, and coming out on the other end. This fiber optics cable is actually the technology that is allowing all of you right now we have an attendee from Germany, and to be able to get those signals from Germany, she is using this transatlantic fiber optics cable that are under the sea. And so it's, again, amazing technology. I will show you just a quick demo of how that works. And then number 4 is kind of an old picture. You see a huge equipment there, and a person dressed in a military uniform looking through something. What is that? Is something called a periscope, and we will see how a periscope works today as well. It is equipment that is very commonly used for military Navy applications. Submarines have them. And we will take a look at the very, very simple simulation sort of that. So the one other thing I want to point out, with demonstrations, we try to simplify and only highlight the important concepts. So real life situations are of course, always a lot more complicated and more, that's why even more interesting than what you're going to be seeing today. So keep studying more if some of these ideas, you like them. Okay, so we're going to move on. Let me. Okay, here's roughly the outline. We're going to review some of the basic optics that we did last time. Phenomena of reflection with the help of mirrors. Refraction, which is when the material is passing through, going from air to some other medium that has slightly different optical properties, and we call that refraction. If you want to review some of these, you can also go back to our first episode, and if you saw the flyer, the WIU Physics YouTube channel link is on there. So, you can always go back and take a look at some of those things there. Then new things we are going to try is now take these elements, but not as singly, but if you have multiple elements, then you can do lots of cool things. So total internal reflection is just one simple extension of refraction. Then we're going to look at multiple reflections, how that helps us understand something called the periscope that we saw that the submarines use. The idea of something called the infinity mirror, then the fiber optics technology. After that, we'll look at multiple refractions, meaning having 2 or more lenses, and how that allows us to understand how a microscope works and how a telescope works. So that's kind of our plan, and it's mostly going to be demos. I'm not going to try to explain concepts through PowerPoint as much today. So let's go back to the demos. We're going to make it dark in the room. And a couple of things I have to do is stop sharing this and mute my
Dr. Kapale, you're muted.
okay, so there's going to be a little bit of an echo, I think. Okay, so I believe you can hear me now. I think there was some audio issue. So what we have is a light source. Okay, hold on, why is that happening? So Jesse, I want to verify with you if we are able to see the 3 light rays and the reflection.
Oh yeah, it's yes. pretty clear, although there is an echo.
Okay, very good. So what we have is the 3 light rays coming in, and you can see think about this being an object really far away. That's why the light rays that we are getting from them, let's say sun, for example, are coming out straight. And think of the extent of the rays as the size of the, some measure of the size of the object. And you can see after reflection, not much change in the distance between the first ray and the third ray. So the size more or less stays the same. The mirror does not manipulate the size. All that it does is changes the direction of the light. Now that was a flat mirror, a nice reflecting surface, nice shiny surface. And you can do that on, at home in the bathroom mirror. Now the surface that I'm showing you is curved, right? So it is curved like that inwards, and you can see the light rays coming in are now being focused at a single point here. And then after that, they actually change position. So the first ray here would be the third one. the third ray here would be the first one, and the second ray just kind of passes straight through. But the fun thing is these light rays coming together. That is what allows us to form images, and that's why this kind of a mirror is useful for building a telescope, if you would like. If you want to try this at home, take a look at a nice stainless steel spoon and look at the inside of it. That is a curved surface, and you can see your image in there. It looks a little bigger than normal, than the standard flat mirror. I'm going to now show you another curved surface that is curving outwards, right? And again, you can sort of see the edge of the mirror here, and you can see after reflection, the rays are fanning out. Okay, and so these are just the basic reflection phenomena that we are able to see here. But now we want to do multiple reflections. So the next thing we are going to try is the idea of a so-called periscope, right? So periscope needs two mirrors, and at the in the simplest design, it needs two mirrors. And here we have one of the reflecting mirrors. You can see it is situated in such a way that after reflection, you see about 90-degree angle between the incident, the incoming, and the reflected rays. And then I'm putting another mirror here at the bottom. Okay, and I have to adjust the angle. So all I'm doing is rotating the mirror so that the reflected rays are about 90 degrees to the incoming rays for this particular mirror. So let's try to zoom in on this, and you can see what's happening here. Two 90-degree reflections, and you get light coming out. So let's see a real life example of this. I'm going to turn the lights on, and my younger son, Apurva, is going to show you a little toy telescope that he built from a kit that we purchased for him.
Here is my toy periscope. You can see that it's just a cardboard tube. There's a slanted diagonal mirror on the top. There you can see it through the hole. There is another mirror on the bottom. Light coming through reflects, goes down, reflects again, and comes out of the back. Looking through the bottom hole, you can see things above your line. So here's a dog right there. I can't see it if I'm crouching down, but if I am with the periscope, I can see it. This is how a periscope works.
Okay, very good. Thank you, Apurva. What we are going to do now is turn the lights off again and hand the camera over to Atharva. So that's your periscope still here. What we're going to do now is show you a different design of periscope. But for that, we need to understand refraction a little better or a little deeper than what we did last time. Right? So I'm going to show you these simple lenses and how they respond to the light, or how they change or bend the light that's coming in. So instead of mirrors, now we are moving away from mirrors to the lenses, and I have something called a convex lens, and you can, let's try to show you the surface here. So you can see the light rays that are coming in are passing through this. So it's a transparent piece of plexiglass kind of material, and it has the two curved surfaces, one outside, one in front and one in the back, and they are both bulging out. Okay, and what that does is it brings the light rays together like we saw last time. You can use this kind of a lens, a convex lens, to form a mirror, form an image rather. And we are going to build a telescope and a microscope with the help of that little later. Now, another device that I want to show you is the convex lens. We have seen that one last time as well, but okay, so it's a concave lens rather. And what we have here is the, again, two surfaces that are caving in, the front one as well as the back one. And with the help of that, you could see the light rays can be made to fan out. They're spreading away from each other, initially parallel and spreading out. And we are going to be using all of these things here in a little bit. So the cool thing about the refraction is instead of having those lenses, I now have a triangular piece of glass slab. Okay, so here you can probably see that. Let me see if that's clear. No. So then let me try a different piece. Okay, I have to turn the light on for a minute. No, okay, I think I found it. Okay, so I'm gonna now, instead of lenses, we want to use flat glass slabs, but not rectangular. Now, these are something that have, this one, for example, is called a prism, and it has a triangular face. Let's do it this way. And because of the shading on there, you can kind of see what's happening. Okay. And the nice thing about these is we can manipulate the direction in which the light is falling onto the surface of the incident surface of the prism. And you can do lots of cool things with it. Right? And this kind of phenomena, if you may know this, was used by Newton to learn that light is made of, the sunlight, for example, is made of different colors. And I think, let me see if I can show that to you. We can see that here. So you have these parallel rays coming in. They're kind of, that's the white light that you see coming in. After the prism, on this side here, after it passes, and because there are two surfaces, there is a little bend. So when light changes medium, goes from air to glass, it bends on that first surface. It bends again on the second surface. And I don't know if you can see this here, but there is some coloration in the rays that are coming out on the other side of the prism. And that is basically the what Newton first learned, and he figured out that white light is composed of many different colors. That's part of the reason this phenomena of refraction is why you see rainbows. So anytime on a if the sun is out and there is rain, if sun is behind you, you should be able to see the rainbow. And this is the kind of the idea behind rainbow. So when you see a rainbow next time, try to think about what's happening and why you're able to see those colors separated. But the thing that is more interesting for us now is refraction. The light is supposed to pass through the glass piece. But if I change the angles, and all I'm doing now is rotating my prism so that it's oriented properly. And what I can achieve by doing that is the light rays now undergo 3 different transformations. So let me point out those to you. First one is a bending at the first surface. Then at the second surface, instead of coming out this way, the angle is arranged in such a way that there's actually something called the total internal reflection. Even though light can pass through this, there is nothing physically that can stop light from getting out. It does not do that. It actually reflects. So this surface, even though it's not a silvered surface, light is reflecting and it's coming out on this side here. Okay, and that is called the total internal reflection. So you have one bend. Let me point out things again. One bending here, another, instead of bending and light coming out, you have reflection at this point, and then light coming out on the other side. And so that's called total internal reflection. And total internal reflection happens to be very useful for design of periscopes as well. So we saw a periscope with mirrors. I'm going to now show you, instead of 2 flat mirrors, 2 prisms, showing you this total internal reflection or the periscope kind of action. Okay, so I'm going to quickly replace this prism with two prisms, one like this. Okay, and you can now see that with the help of one prism, I have been able to, okay, let's look at that. That's the prism. Get almost a 90-degree reflection. And then I am going to put another prism here, but I want to increase the distance. So the rays that are coming out, I want them to be kind of far away. Okay, so you can see, so the idea is, imagine that this is part of a tube, right? So you have a tube that lets these that basically protects these light rays, and then there may be some obstacle here. So your eye is over here looking at something, even though you may be behind the obstacle that exists here. And you are able to see things, for example, from a Navy ship, submarine, even though when it's undersea, you could see things that are outside. And that's kind of cool. And now, of course, the modern, the big telescope, the big periscopes that they use for commercial purposes are a little bit more advanced. They may use kind of a telescopic technology as well. So in addition to these reflecting surfaces or prisms, they can also employ lenses to be able to magnify or to be able to see faraway things. So that's basically combination, if you will, of a telescope and a periscope for that purpose. So what we are going to do now is these multiple reflections that we talked about, either with the help of the mirror or with the help of prisms when they are arranged correctly, where we are using the phenomena of total internal reflection. I want to point out that last time we were talking about a concept called refractive index. It's a property of the material, like glass, for example, which allows us to quantify how much it causes light to bend, right? So it's just a mathematical notion that allows us to quantify how good a certain material is at bending light. And so that can be used. And so in one of our labs, research labs here, that idea coupled with this total internal reflection concept is actually used to measure refractive indices of new materials that are built in the lab. And so that work is done by Dr. Babu and Dr. Malur. And if you have questions, you can ask them certainly about that. So let me show you one more cool thing about the total internal reflection and its connection with fiber optics. And then we're going to show you some toys that my son is. Okay, so what I'm going to do now is turn actually the light source off. We don't need that for this purpose. And I have a pretty bright green laser pointer. Let me find that one. Okay. Here it is. And what I have, let me turn the lights on so I can show you what we are seeing just for a second. This actually even works well with the lights on. So the device that I'm trying to show you is basically just a glass tube, but that has a straight glass tube for, in the beginning here, and then it spirals. And then it bends up and comes out here, okay? And I'm going to now basically shine a laser through one side and see what happens. And it will look much cooler when I turn the lights off. And again, that's my, okay, here we go. And my laser is on. And you can see it glows pretty well. If you look at these points here, you can see the light actually bending, reflecting close to the edges, and then changing its direction, reflecting again multiple times, and it's able to come out. You can see the other end of the tube pretty bright. So the light is passing through the bent material and is able to transmit. So the analogy for this, this is a pretty cool technology to be able to change the path of the light in such a dramatic way, right? Because you are able to bend it, make it go around a circular path. You can do that with electrons, and that's how our old technology used to work. We would use electrons passing through electrical circuits to transmit messages. But now, of course, right now, if you are on the other side of the Atlantic Ocean, you're using something called transatlantic cable. Something like this, of course, this is just a simulation of a single fiber. They have lots of fiber bundles all together in a very protective kind of case so that it does not get damaged when it's under sea. And that's what, in terms of light pulses like this, it is passing on this medium to you, right? And if you are on the other side of the world. And I think my father is joining from India, and I have a niece who is joining from Germany. So we are truly global and seeing the demonstration of a technology that allows us to connect this way that we're doing right now. And of course, our conversation is passed through in terms of light pulses, not like these fast, but this is just a simulation again. So now what we are going to do is take a look at these multiple reflections and show you kind of a couple of cool things that multiple reflections allow you to do. So here is my elder son, Atharva, and he has a few things to show you. So there you go, Atharva.
All right, so.
Okay, so he's just powering on the device that he has.
All right, so look at this. It looks like a strip, and then it goes on forever and ever and ever backwards. And it looks like you can stick your hand in there, and you still won't feel the bottom of all the light strips. Well, it's really not that, because see my hand here, it can't be like the tunnel. So this is called an infinity mirror. So behind this light strip we have a mirror, and then we have the light strip, of course, and in front of that we have a two-way mirror allowing us to see inside, along with reflecting the light back. So the mirror we first have behind the light source is reflecting the light back into our eyes, but then since that's a two-way mirror, it reflects it back and forth, allowing it to make this sort of infinity pattern. So as far, like when you go look further, the object looks smaller, because the farther the object, the smaller it looks. Kind of like if you're a couple hundred feet away from a tree, it will look smaller than when you're like right next to the tree. You will be looking up and you wouldn't be able to see the top of it almost. So that's how this infinity mirror is. And now to look in further depth of how it works, you're going to use this dog here and these two mirrors. So we're going to place this in at 90 degrees. And then we're going to put the dog facing in here. So now so the dog's now facing the center. And now how many dogs can we see? So there's a dog over on this side, and on the back over down there. So we have 4 dogs looking at the center. Now let's decrease the answer a little bit. All right, now that we have decreased the angle, now we see 1, 2, 3, 4, 5. We see 5 dogs. Now let's decrease it even more. Now we see 6. Now 7, 8. And now if you decrease it anymore, that we won't be able to see it much. So now to explain exactly how the infinity mirror toy that we just looked at, we have these 2 mirrors again, and then we have the dog. So then the dog's facing over this way, And now we see that the dog is reflecting in here, which reflects the light back into this other mirror where you're looking at right now. And it goes back and forth, which allows it to make that infinity pattern and make it look like there's a bunch of dogs going up till forever and ever and ever and ever. All right, so that's the infinity mirror.
Okay, thank you, Atharva. So we're going to go back to now the dark room and just show you quickly. Okay, hold on. Let's not turn it all the way off because I want to find my elements first. Okay, so what we're going to do is just give me a few seconds to set up here. I'm going to now quickly simulate for you the next set of concepts, which are now using the lenses and the mirrors. First, we will do it with the mirrors. So I'm going to now try to replicate how a telescope looks like, how the telescope behaves. But before we do that, we actually need to understand how our eye works, right? Remember I said in the beginning, our eye has a lens, and that lens actually has a remarkable ability to change the focus. So what do I mean by focus? Let's first kind of think about that. So I have a lens here that is sort of like a like the lens of an eye, right? And you could see that it's bringing the lights closer together. The point where the light rays are coming together, that's called the focal point, and the length between the center of this lens to that point is called the focal length, right? And so our eye can actually change that focal length. It's like suddenly being able to use, let me see if I can find another lens, which I had here. Okay, sorry. It is difficult
I don't know, I can find it for you.
It is difficult. Okay, here we go. It is difficult to know where things are when it's completely dark in the room. Okay, so our eye can do this versus that, which now has a much longer focal length, right? And so it's able to do this to be able to focus at objects that are at different distance. Of course, this distance doesn't change. You always want this rays coming together on the retina, which then sends a signal to the brain to interpret what that image is. So that's something remarkable about our eyes. Now, because our eyes work that way, the single lens devices are not pretty good for making, telescopes and microscopes. For this one, for example, you could bring that image there. Then our eyes do not like these diverging rays. It is a hard work for our lens in the eye to bring those diverging rays to come together to form an image. They want parallel rays coming in, and that's why we are doing a couple of tricks here to be able to show you how the telescopes and the mirrors work. So a simple refracting telescope actually has two lenses. So I'm going to show so here's a lens that has a slightly larger focal length, and then I bring another lens, and all I have to do is adjust its distance from this point so that the rays coming out on the other side are parallel. Okay, so I'm just going to quickly do that. And you can see right now, they're not quite parallel. They are actually diverging. As you can see, they're separating, going away from each other. If I go too far, then they start going. So let me just do it this way. I need to do some adjustment here so that I can get a longer ray path. Just give me a second. There we go. Okay, and so let's show you what, again, I want to adjust the distance so that the rays coming out on the other side are not diverging like right now and are not converging like they are right now. It needs to be somewhere in the middle when they come out parallel. And that's the distance where if you now keep, that's the distance for the second lens, where if you keep an eye on the other side, you will be able to see a faraway object, right? So this would work as a telescope. Two lenses, one that has a longer focal length and one that has a shorter focal length to give you the image of a faraway object. Now, other thing I would like to point out here is that the distance between the rays on the edges here is little larger than over here, right? So the image, of course, is going to be smaller than the object that you're looking at, but it's nice that you're able to see it. And of course, you can play with the focal length of this lens to increase the magnification here. Now, what I'm going to do is just a simple thing. Interchange the positions of these two lenses and let's see what happens. And I will hand, okay. So all that I'm doing is I have some markers here for me. And then all I'm going to do is the small focal length mirror is going to stay, lens rather, okay, small, because this distance now is smaller. It focuses the light quickly. And then the other lens, okay, sorry, there is some challenge here. Hold on, Atharva. Atharva, can you come from that side? Okay. Okay, I think we have it now. Okay, so what we have now again is the lens position interchange. So a thicker lens in front and then this way here. And you can now see if I place the second lens at the right position, the rays coming out on the other end are again parallel to themselves. That's the thing that we want. And if you look at here now, the size of the object is smaller than the size of the image that you would see in your eyes. And that's how a microscope works. So the telescope and microscope, they're basically just interchanging the properties of the lenses. And they all work kind of the same way, if you will. So I'm going to now quickly, in a minute, show you a quick demo of that, because what you saw so far is just how the light travels. I wasn't really able to show you an image, right? And without that, seeing the image, you miss out the cool factor. So we're going to now turn the light on for a little dim here. I have a little light source that I'm going to show you quickly. Okay, so here's the light source. So it's a F. There is a reason why it's a F, because if the image is not upright like that F, you can tell. If it was an E, you couldn't tell. If it shifts left and right, you can tell that as well. And then just like I did the ray passing demo, I have a lens here, and that has a smaller focal length. A larger focal length, because I'm trying to simulate a microscope right now. And then I have another lens here at certain distance that is that has a smaller focal length. And you could see on here a much larger image of the object. So let me point out what's happening. I'm not using any zoom in or anything. You saw what's the size of the object is, okay? It's occupying a very small region of the screen. And then if you look at the size of the image here, it's much larger, right? And that is, of course, much easier to see again if I turn the lights off. And this larger image, okay, is the result of this microscope structure. On all I'm going to do now, I will give the camera to Atharva, and you can keep seeing that all I'm doing is replacing these two mirrors, just interchanging them. So sorry, the lenses. So the first lens here and the second lens there. And now we will see what happens with the image. You can see, let's again turn the lights off. You can see the image now is much tinier. So that's now how a telescope works. You have, again, a faraway object. You have a certain combination of the lenses, these two lenses, and then you get an image on the screen that's, again, shifted sideways. Of course, if you were to look at it through your eyes, you would actually have to bring your eyes right after the eyepiece, which is the second lens. That is always tricky to show on a phone. I cannot bring my phone there to show you how your eyes would see it. So I have to come up with a trick. I had to come up with a trick to project it onto the screen with some manipulations. And that's what allows us to see how the image would look like. So the image in our eyes would look like it would be upside down, and it would be left-right shifted. Okay, so for if you are looking at, say, moon, for example, here it doesn't follow all. It looks upright because the rays have reversed in the process of trying to project it for you on the screen. So let's now. So what I have done so far for you.
Dr. Kapale, you're muted. Okay.
So just to recap, a quick recap of what we have done so far, we have used these optical elements to show you paths of rays, and as well as how the image formation works and how our eye helps with that image formation process at the last step of a microscope and a telescope. So now I'm going to take you to Dr. Wong's lab, and he's going to show you a real microscope and some slides from some of the cells that he has. Okay, so Dr. Wong, take it over.
Yes. Okay, can you see me?
Yes, very well.
Okay. Wang's phone is what we are. We have my student Dylan. He's helping me to show everybody the function of a so-called polarizing microscope. As we have just seen, the microscope has optical lens which use a very small lens system with very small focal length. The idea for the microscope is magnification and resolution. And fortunately, to achieve such two goals, you need to have the lens which has very tiny focal length and a relatively large diameter. So D over F is determining the resolution. And we have different objectives, and its magnification runs from 25 to 63. And we have some advanced objectives which can magnify 100 times larger. Such kind of objectives usually use oil as the liquid medium between the slides and the lens. And we didn't set this up here, but the microscope can, the objective lens alone can magnify 100 times. And usually you have this eyepiece, which is the second time magnification, and which is 10 times. So you have 1,000 times of magnification for a normal biological microscope. And that means 1 micrometer, which is almost the resolution for all the microscopes, can be enlarged, magnified into 1 millimeter. So our eyes can see it. Okay, so today I'm going to show you how more advanced type of microscope, which is called the polarizing microscope, or somebody call it polarization microscope, works. So here you see we have the light source. The light source with some of the lens system. This lens system only focuses the lens into a small spot. I will lower my stage down. Small spot on the sample. And this sample is an onion skin. Onion skin is just the onion we eat. You just peel off the yellow or brown part of the skin in your kitchen. And we're going to see what is inside the skin. So you see this brown piece of onion skin. And we have this object lens. It has 25 times the magnification, 0.4. I think this is some called aperture. Okay, so this will imitate the first step in the meter somewhere there, and then you have eyepiece to look at it. Let's look at the magnified image. And today we don't go through there, and we have a advanced camera. This camera is connected to my computer. So let me first try to see, let us first try to see what is actually inside the onion skin. So I am adjusting the position of the specimen so that if this guy is close to my lens currently using, I will see some image on my camera. Oh, it seems that it is too bright, so let me After we see the image, we can switch to the computer. Okay, very good. So maybe I can use a even smaller lens so that we can see a large part of the onion skin. Okay, on my computer you will see
Are you planning to share this computer screen now?
Yes, let's do that. So we don't need the phone, and I'm going to go to the computer and let's try to share the where I'm on. So this
bottom, the green.
This one, right?
No, on the bottom.
This one.
Right there.
Also share screen.
Yeah.
Share this one. Yes. Okay. Can everybody see my computer screen?
Yes.
Okay. Very good. So you don't need my cell phone anymore. So let's see. My cell phone I still need it for the audio, right? So okay. So I'm adjusting the position of my slides up and down. When it hits on the focus of the objective, we see the image. Now the magnification is on the other side. I think it's 25 times larger. So it's smaller magnification. You see a larger area of my onion skin, and our goal is to see some of the structures inside. And you see the onion skin. This brownish color is the great background, and then you see a lot of, can you see my cursor?
Yes.
Yeah. So you see the cells. I'm cursing the cell walls. So these are the walls, and it's so interesting, so apparent that in each of the cells, these cells are dry cells. By the way, the fresh ones are also good. The fresh one actually is better, but the fresh one won't last for 1 or 2 days. So you have the dried walls, and which is typical for only plants, not for animals. And then in each of the dried walls, there's some structure. Many of them has dried, but you see bricks. Looks very much like bricks. It seems that each cell has one crystal inside. Some of the crystal has baby crystals there. And why not let me magnify it more into the next stage? So I magnified to the next stage, which is that was 4 as 10. This is 25. This is 25 times larger. Okay, and I need to increase the background light. So because we are now focusing on only a small area on the onion skin, and we need more light. And now it is so apparent, right? We have the cells. Each cell has some crystal inside. And the crystal sometimes has some other baby crystals inside. Okay, what are the crystals? These crystals are called calcium oxalate. It's just very similar to the rocks we have in the mountains or anywhere we have. It is calcium. It's not carbonate. Carbonate is CaCO3. We know it very well. Those are our rocks mostly. But it is oxalate is also CO, but it's not the CO3 ions, and it's softer than calcium carbonate or than the rocks. And the mechanism is when the cells, when they are growing, they need the calcium. Everybody needs calcium. It falls into our structure. By the way, we do have minerals or crystals in our body. The bones occupies a large portion of our cells, right? This calcium oxalate is stored here because when they are grown, the plants has more calcium. Too much. If you have more calcium than needed, then they will store it. This is the storage room, and it's so interesting that they grow very, very perfect crystals over there. And when the plants need more calcium, and some researchers say that because this kind of thing, crystal is not so hard, they will just absorb again the calcium from the stored crystal. Okay, our goal today is to discover the size, orientation, and the crystal structure of the calcium oxalate. The polarizing microscope allow us to shine polarized light into the specimen. So let's try to discover a little more. So this, I have the unpolarized light. If I shine the light with polarized light, and let's see, shine light with vertically polarized light, and I want to look at the specimen using the horizontal polarized light. For a normal specimen, if I have a piece of glass or I have whatever piece of normal isotopic material, if you trying to use horizontal polarized light, then trying to use vertical polarized light, then there's no horizontal polarized light passing through. And because this light does not change its polarization when transferring through the specimen. But if you have a piece of crystal, the optics physics happens inside is this vertically polarized light inside the crystal will be split into two parts, one at 45 degrees and the other at the negative 45 degree oscillation. And then the crystal will induce a phase difference between them. The initially vertically polarized light will be transferred somehow into horizontal polarized light, depending on a lot of things: the speed of the crystal, orientation of the crystal, and the thickness of the crystal. So this species we cannot change this, or this calcium oxalate is already, but the thickness and orientation will define how much light is transmitted. So I'm going to insert my
So what Dr. Wang is doing right now is putting polarized sunglasses on the microscope, right?
Yes.
And the cool thing is you're able to change the angle of those sunglasses, and it changes the contrast.
Okay, so now suppose my input light is vertically polarized light, and I insert the horizontally polarized polarizer. You see the background. Background are mostly dark, right? But those bricks and those crystal structure is now apparent. And the brownish color tells us the thickness. When the thickness is 0, then everything is dark. And when it's thicker, it goes a little brownish, and there's a color sequence is on my wall. Maybe we can show you later use the phone. So this color sequence tells us how thick the crystal is. Now, the orientation of crystal also determines how it appears. So let me turn my stage and let you look at this 3 or 4 pieces of crystals. So I will turn the crystal in 360 degrees. You see, apparently, when they align with either the polarizer or the analyzer, it just totally disappears, right? When they are horizontal or vertical, they become dark. When they are at 45 degree or negative 45 degree, they become bright. So I have a lot of dark and a bright image, right? So this is a very good feature to show that they are really anisotropic crystals. Let me lock it and put it into the center. Now, we discover these crystals by turning the stage and make them appear and disappear. The background will always be black, but the crystals will be bright or dark, depending they are 45 degree or 0 or 90 degree. Now, to see the thickness of the crystal, and we need to study the colors. This is very interesting. So let me magnify it more into. This is 40 times. That is good. Good magnification. So I magnify the crystal 40 times larger, and I see the color. Now you see, actually, you can see the edge of the crystal, and you see the size of crystal by if I measure. I think the size of a crystal is on the order of 20 micrometer. It is still smaller than the hair thickness of our hair. So one piece of crystal is about half or quarter of the size of our hair. And to see how thick the crystal is, of course, there are some more better facilities. For example, electron microscope, you can shine electron on it and you can measure the actual size. But in our case, we cannot see we can see the X and Y, we cannot see how thickness, the Z definition. We see its color. So under this crossed polarizer is brownish. And if I change the polarizer, brownish cross polarizer means that I have vertical in, horizontal out. What happens if I have vertical in and vertical out? And this makes things, I found this is more interesting than the other case because this gives you more colors. So if I have vertical in and vertical out, so what is the color left after it transmits through my polarizing analyzing system? And see the color is should be light bluish or light greenish. Green is actually thicker than blue. And again, this color depends on the orientation of my crystal. So at a certain angle, this color will be merged into the background. At 45 degree and negative 45 degree, and the crystal appears more vivid. So you study the color using the horizontal analyzer, then using the vertical polarizer. I have a brownish in the cross polarizer, and this bluish, light bluish in the parallel polarizers. By comparing to the color chart, we know how thick the material is. So this guy gives us something like 400 nanometer of delay. 400 nanometer is about one wavelength or half a wavelength. So it's a little more than half a wavelength of phase delay between the two modes of light in the crystal. And that means the delta N multiplied by D thickness equals a little more than half a wavelength. This delta N, the change, the birefringence of a crystal is around 0.1, 0.2. Then the thickness should be twice or 0.1, 0.2, you go to 0.1 is too large. So let's see, 0.1, 0.2 is the more birefringent crystal. So the thickness should be on the order of 10 micrometer. So the thickness is somehow comparable to the width of the crystal. It's our best guess. And why not? Let's go back to see a lot of other crystals and see. Okay, I'm going to make the. Okay, now I dim the light and I have a lot of other crystals on it. And you see that each crystal may have different orientation, a little different orientation, different X, Y, and even different Z size. I mean the thickness. And I'm going to turn the background. You see how they change in color. And it's like the stars on the sky. And you turn your head around and you see different color. They change their colors. From the color pattern, you see their thickness. Okay, and this is mostly how a polarizing microscope can be used to finally study some specimen which has a crystal structure, so that polarized light, for example, the vertical polarized light, when it passes through the crystal, it can be somehow changed to a combination of vertical and horizontally polarized. And then you study the differently polarized parts, especially the color of those transmitted light. You know what is the species of the crystal and how thick it is and how it is aligned. And today we have the regular crystals in the iron skin. It's easy because I already know that what is the principal axis of the crystal. But if you have a crystal with irregular shape, it's a random shape, then this kind of polarizing microscope is much more powerful. Okay, and that is
wonderful. Thank you, Dr. Wang. What we are going to do now is, when Dr. Wang stops sharing the screen, we are going to now show you a real-life telescope. Natalie, who is Dr. Araja's student, she's going to show some pre-recorded videos of the telescope viewing in the nighttime, and she's going to tell you a little bit more about it. So, Natalie, take it away.
All right.
You will have to unmute yourself first.
Hello. Okay. So, all right. So, everyone, hi. So, I'm Dr. Araja, and yeah, we'll be showing you a little short, really short videos about telescopes. I know we are about the time now. What we do in my lab is working with radio telescopes, so doing kind of the same ideas that they had been described today, but in microwaves, not in optical light. And Natalie is working in my lab, and she prepares some videos that explain a little bit about the telescopes. So Natalie, just in the interest of time, I think we will be showing some of the videos at the beginning when you talk about some of them, and then we go with the one of the moon. Are you there?
Yeah, I'm here.
All right. So if you can introduce yourself and you let me know when to you want me to start the video.
All right. Hi, I'm Natalie Kovacevic. I'm a senior here at WIU, and this is one of the videos that I recorded in our WIU Astrolab. So you can start the video. So this is Orion. He is our 10-inch diameter reflecting telescope. And so what I'm showing here is that how the reflecting telescope works. There's a big mirror in the back. So light is going to come in, hit this tiny mirror, or hit the mirror in the back, and then this tiny angled mirror here. And then the light is going to get reflected into the eyepiece here. So basically the reflecting telescope uses mirrors, like how Dr. Kapale was talking about earlier. And then so in this video, I'm showing actually using the telescope to look at Thompson, which is the dormitory right across from Kearns Hall, using Orion. And so I already had it nicely set up. So I just, it's kind of hard to see. It's kind of hard to put the camera to the eyepiece and show it, but you can see Thompson a little bit here. And this is a pretty clear photo. You can also, change the focus to make it more clear if it's blurry. And like right here's where you change the focus of it to make it, blurry or as sharp as you want. But yeah, so that's the dormitory, Thompson. And then so when you're getting ready to look at an object, what you're going to want to use is this thing called the finder. And what the finder does is it makes it just easier to look at an object. So you look through this little thing called the finder, and it basically has like a bigger image of what you want to look at. So that way, when you look through it through the telescope in the eyepiece, it's just, you're already pointing the telescope at that spot. So all you have to do is just do minor adjustments to actually see the object you're looking at. So again, we were looking at Thompson. You wanted to go through the finder first to make sure we were pointing at Thompson, and then look through the actual eyepiece and do those minor adjustments, and then you can see Thompson very clearly. And then so this is the refracting telescope, which is different from the reflecting telescope. Now, if you remember what Dr. Kapale was, showing us about the refracting telescope, is that the refracting telescope has a lens here, and so because of the lens there, and it has a very long focal length, so which is why the telescope is much longer than, say, like this telescope is so much more longer than the reflecting telescope because of the fact that it has a lens instead of a mirror. So when light goes through the lens, it has to travel the whole focal length, which is the whole length of the telescope. So that's the main difference between like the refracting and reflecting. And then here I am using the reflecting telescope to look at the moon. I did this the other night when I was back at school. We got it nicely set up and everything, and already pointed at the moon, found it using the finder, and then made some adjustments to, really get a good, picture of the moon in the telescope. And you'll see that in a second. It takes me a little bit again to show good photos because it's kind of hard. But yeah, here's here's a couple like shots of the moon where you can like really see like the craters of the moon and everything like that. And yeah.
All right, thank you, Natalie. Yes, and those are some of the telescopes that we use for outreach activities in the Astrophysics Research Laboratory. Dr. Kapale.
Okay, all right. Thank you very much, Dr. Raja, Natalie, Dr. Wong, and Dylan for helping with today's presentation and showing the real life things. And as hopefully you all saw, the real instruments are a lot more complex than the simple simulations that I showed you, but hopefully that gave you some idea of how optics works and how optical technology is shaping our world. You know, the fiber optics is one good example. We're talking about driverless cars. It cannot have been possible without the understanding that we developed of the field of optics. They use in some cases they use radio waves. Some cases they use lasers, and so combination of all of these. But basically, basic simple optics concepts put together forms the technology of that will one day allow all of us to sit back and relax in our cars on long cross-country trips, if you will, without having to worry about the road conditions in the driving. Okay, all right. So that's it for now. Thank you all for joining. Feel free to submit questions. They will actually be stored. So if I don't get to answer them now, we will be able to answer them later. So you can comment or put questions in the chat,